After developing an understanding of oxidation, reduction, an oxidizing agent, and a reducing agent, what we can do is start to look at how these chemicals behave relative to each other. The example in the last video showed a single replacement reaction that happened to be spontaneous. And one of the false assumptions that we make in early courses like Science 10 or Chemistry 20 is that any combination of an element reacting with an ionic compound should instantly produce some kind of a viable product. And that actually is not true. There's an additional criterion that was not introduced at that time that we're going to flesh out here. So the assumption that we're trying to figure out and maybe falsify is that all single replacement reactions are spontaneous. One of the ways that we can do that is by undergoing an activity series test, kind of like what's shown here. So notice that we have a series of oxidizing agents that are being tested. Those are shown in their ionic form. There would, of course, be some kind of a balancing entity in there, whether it's chloride or nitrate or something. And there are samples of different reducing agents shown in each well of this spot plate. Now, it's hopefully pretty clear to see that many of these containers appear to be going through some kind of a visible change, whether it's turning dark, having the color of the solution change, but in other cases, nothing really appears to be changing, and that's actually very interesting. So if every single one of these single replacement reactions were spontaneous, all of these pieces of metal would turn dark, and clearly that's not happening. So what we can do is use a test like this, where we're checking on an activity series, in order to deduce which of these agents are strongest or weakest. What we would do normally is just have a look at the couples involved here. And this particular set of information doesn't really couple everything off really well, but it still gives us the idea of an activity series. In other words, do we see which of the metals specifically appears to go through the most reactions? In other words, which of the metals appears to have been darkened the most? Arguably, that looks to be magnesium. If we then have a look through, it looks like zinc was affected next. After that would be something like tin. And lastly, it looks like copper is reacting the least. So it gives you a little clue as to what we might be looking at there. This may not be the best image in order to pull this information from, but the lab that goes along with this section actually is very compelling in terms of the data that could be used to predict a reduction table. This being said, remember that reduction is gain of electrons, and these metals are actually not really good starting points in order to figure out what's going on. So if we want to build a reduction table involving a bunch of substances gaining electrons, what we actually need to do is start with a series of oxidizing agents that indicate the relative strength of those oxidizing agents. So looking at the OAs, the oxidizing agents up here, the one that appears to have made the most darkened colors is actually silver ion. Okay. Now, it's maybe difficult in this particular context to understand what it would be coupled with, so in a future slide we can actually find this on the table that we would pull from our data booklet. But let's assume correctly that the silver ion is our strongest oxidizing agent. What I'm going to do is I'm going to write it at the top of my reduction table as the strongest oxidizing agent. I will, for lack of more information, couple it with its metallic counterpart, which we'll see in a little while that that's correct. And then what I can do is look at the charge of this half reaction and add enough electrons to make the charge balance. After this, the next most reactive oxidizing agent is copper. So I'm going to take copper 2 ion, couple it off, and add enough electrons to finish up that half reaction. Okay. Now in this image, I've actually cut off a little bit from the original source that showed that zinc actually does have a tiny little bit of a reaction that takes place over top of, what otherwise looks like a non-reaction there. This also, when we do the lab, will be fairly subtle, but there would actually be a reaction there. And this will be confirmed when we look at the table here in a moment. The next least reactive, or I guess next most, since we're talking about strength, is magnesium. And arguably at this point, it's kind of hard to tell between magnesium and zinc what order those should be in, but we'll see in a moment that this is accurate. Okay, and then if we wanted to just complete the exercise, we could have sodium down at the very bottom. So this is the formation of a reduction table by taking empirical evidence, like what we would find in a lab, and assessing in a rank order which oxidizing agent was the strongest, and then ranking them in order of strength of reaction. In other words, which one had the most reactions, put that at the top. Which one had the next most, put that one step below, and then kind of keep going all the way through there. So the OAs are going to be listed here with increasing strength in this direction. What's interesting then is that we would, on the right side of the table, actually have a bunch of reducing agents. These reducing agents, in fact, become more reactive towards the bottom, and so my strongest reducing agent is actually here, and my strength increases as I go this way. What we can notice out of this is that anytime that the oxidizing agent is in a position of strength relative to the reducing agent, which is to mean that as we go in this direction, the OAs become stronger, and as we go in this direction, the RAs become stronger. As long as the relative position of the OA and the RA are in positions of strength like this, this indicates that the reaction would be spontaneous. And we should see some kind of discoloration of the combination of substances as a result. On the other hand, all of the non-spontaneous reactions could, in the case of something like copper reacting with itself, indicate that there's no net reaction, but more importantly, could occur if you have a weak OA trying to react with a weak RA. So if these substances are in a position of weakness, as I'm indicating here, this reaction is non-spontaneous. So what we can do at this point is use this understanding of how to construct a reduction table, the implication of which orientation of OA and RA produces spontaneous reactions versus non-spontaneous reactions, and actually do a number of very useful things with them, which are first to build reduction tables with more sparse information, or eventually to predict reactions altogether, which is going to be a future video. So the summary of what you're seeing here, reduction tables involve a series of reactions of substances, OAs, that are gaining electrons, showing the strongest OA at the top on the left and the strongest RA at the bottom on the right. So this is the reduction table that is found in our data booklet. And just to point out that the 4 substances that we did have in the previous slide, which were silver ion, copper 2 ion, zinc ion, and magnesium ion, do appear in that very same order. Okay. So I might suggest then that for your own gratification, you do the same kind of markup on your table, indicating that your strongest oxidizing agent is here. Do a big arrow up along the side and show an increasing strength that way. Your strongest reducing agent is way down over here, and we get an increase in strength that way. What's interesting then is that through a lab, we actually deduced the order of these 4 things ourselves. We didn't have to refer to this table. However, what the table is showing is that there are lots and lots of different half reactions that have been tested for us and arranged in sequence. And in fact, this table is a smaller portion of all of the reduction half reactions that exist. I'm sure new ones are being figured out every day. And it is possible then to have to deal with half reactions that don't even appear on this table, and I'll show you that on the next slide. So imagine that our job then is to take the information here and arrange it in such a way that we create our own reduction table. And if you're thinking to yourself, I can kind of cheese this, I can just look for these substances over on this table. Well, these substances have been chosen specifically because the half reactions cannot be referenced, at least in the table that we have. So your job is going to be to apply your understanding of the reduction table and your interpretation of a spontaneous and a non-spontaneous reaction in order to construct your own reduction table. One thing of note is that occasionally there will be specific labeling of spontaneous and non-spontaneous reactions, but in this case, I would suggest that phrasing like this is actually interpreted as a reaction that's non-spontaneous. So both of these reactions, therefore, are spontaneous. Okay? Now, as a result, you may feel uncomfortable with dealing with that first first reaction that's shown there because it doesn't actually show you anything about the redox couples. And hopefully you picked up before that redox couples are going to be the foundation for figuring out what's going on with the table and therefore the relative positions. In this case, what I'm going to do is I'm going to skip over what I'm going to label reaction 1 because the information for right now appears like it's incomplete. We can sort it out a little bit later. If I go to what's labeled reaction 2, I notice I have enough information to deduce redox couples. I see that manganese ion, 2 ion, is coupled with manganese, and lanthanum is coupled with lanthanum 3 ion. So these redox couples help me to figure out the substances that I'm going to put into my table, and the spontaneity that I imply over here tells me about the relative positions of them. Remember that a spontaneous reaction has the substances in position of strength relative to each other, and a non-spontaneous reaction has the substances in a position of weakness. Really, at this point, what we're going to need to do is figure out between the manganese 2 ion and the lanthanum which of these is the OA and which of them is the RA so that we can then seed them into our table. Now, the way that we do that is not really to compare them to each other, but rather to compare it to the redox couple. So when you look at a redox couple, the entity that has the more positive charge is going to be your OA. So when comparing manganese 2 ion to manganese in its elemental form, manganese 2 is the OA because it is more positively charged. Since every redox reaction must react an oxidizing agent with a reducing agent, we really don't even need to repeat the exercise with lanthanum. We can just assume right away that that's what the lanthanum behaves as a reducing agent. Okay. However, if you did check on it, you'll notice that the lanthanum 3 ion over on the right is the more positively charged substance. Technically, that would be on the left side of our table as an OA, and confirming that the lanthanum metal is the reducing agent. So let's overlay this into the fact that the reaction is spontaneous, and we're going to have a look at this arrangement here. Okay, so the oxidizing agent wants to be in a position in our table that's higher than the reducing agent. I'm going to take my reducing agent first. I'm going to couple it. And then I will balance it for charge. And what I want to do is take this now completed half reaction and, due to the fact that the reaction is spontaneous, seat it higher in my table than the lanthanum half reaction that I'm going to create. So I put the lanthanum as a reducing agent in a position of strength. So I want that reducing agent to be strong. I'm going to couple it. Balance it for charge. And I'm done with this particular portion of the exercise. Once you have this base, pretty much everything else can be built away from this arrangement. So the next step that I'm going to do is look to see if there's a comparison between a new element and the elements that are already seated in here. So if I look at reaction 1, I see that manganese ion is being compared to copper. So since manganese is already on my table in this position here, then I can use that to my advantage. Let's have a look and see what we can read from that information there. Since manganese 2 ion has already been identified as an OA, I know that this substance is acting like an OA. The copper metal is going to act like an RA. And in fact, if I cheat a little bit and I look down over here, I can deduce the redox couple that's specific to this set of circumstances. So that gives me an idea of what it is that I'm going to write in next. But now I need to focus on the fact that the reaction overall was non-spontaneous. Okay? If I direct my attention to the placement up here, this means that we want the OA and the RA relative to each other to be in positions of weakness. So that means that the reducing agent copper metal is going to be placed above the manganese ion. I'm going to couple it off as I identified with copper 1 ion and balance the half reaction, and that's good there. Okay, the last thing I need to do is have a look at equation 3 and see what I can figure out from there. Now, this one is a little interesting. The redox couple for cerium is nothing like we've seen before. Seems like everything up until now has involved half reactions having a metal ion turning into its metal, and this will definitely give us a different look at how to construct a redox couple. However, using the same types of tips that we had before, if I wanted to focus on cerium as a reactant and then cerium as a product, you'll notice that the reactant side has it in its 4+ valency. On the product side, it's 3+. And as suggested at least a few times now, the more positive of these entities is going to be the oxidizing agent. So that means that the cerium 4 is the OA. We could have also figured this out for the fact that copper metal is already on the right side of our table. So that is confirmed to be the reducing agent. So how do we know where to put the cerium in the table? Since the reaction is spontaneous, we want the position of the OA to be in a position of strength, and the copper relative to that also to be in a position of strength. So having this, you might call downhill reaction taking place. So I'm going to take the cerium, I'm going to put it up at the top here. Because it is above the copper metal, then both of these relative to each other are in positions of strength. I'm going to couple it, and then I can balance for charge. This one is a little bit unusual because both sides are charged. So all that I need to do is add enough electrons to the reactant side to make both sides equal. In this case, I actually only need to add 1 electron to change the 4 positive cerium to be equal to the 3 positive. So essentially 4 positive minus the 1 charge from the electron is equivalent to the 3 positive charge. Now that we've learned how to construct reduction tables and interpret them, what we can do now is learn how to figure out balanced redox reactions from this information, and that's eventually going to take us into some chemistry 20 stuff with respect to stoichiometry.